Okay, so yeah, if you want to type in your name to the chat, now it's being recorded. So we'll get your name for the data. Okay, welcome everybody. I hope you and your families are all doing great. And happy Census Day. So I just learned this today, that it's a Census Day. So yeah, it'll be interesting. What's the population of Liberia now? About 4.5 million? Something like that, I think. So yeah, so we'll see what it is afterward. I think it's 4.5 million. Okay, let's wait one more minute, and then we'll start up.
How was the weekend?
Oh, it's a good weekend. How are you?
Thank God.
Good. Yeah. We got another weekend coming up. So all right. So let me mute everybody. Okay, so again, if you wanna unmute to ask a question or say anything, please do so. All right, welcome everybody. Thank you again for being on time. I hope everybody's network is okay. I hope you all had a good week and a good census holiday. And yeah, so we're gonna continue today talking about the material about matrices that we did last time. So we'll go over the homework, which I think is a little bit easier this time than some of the other ones. But before we go over the homework, just want to recall that all of this homework is about matrix multiplication, right? So remember what we had. If we have an m by n matrix and an n by p matrix, then we can take their product together, and that gives us an m by p matrix. And I mean, writing it out this way, you know, the jth entry in the ith row is given by taking the dot product of the ith row of A and the jth column of B. This is a little bit, you know, complicated to see just from the definition. But the idea is that if you have A is your matrix here, I'm not even going to fill in the numbers, and B is your matrix here, then AB fits right here. And the way that you get some element here in AB is that it's going to correspond to a column of B and a row of A, and you're going to take the dot product in order to get the actual entry here. Okay, so since we have practice on the homework, so let's just go do the homework so we can get into the topic from today. So first the first problem on the homework, we have two matrices A and B. So A is 1, 3, 0, 5, and B is -1, 1, 2, 0. And what I want to do is compute their product, but in both directions, right? I want to compute A times B, and I also want to compute B times A, right? So yeah, so I want to do A times B and B times A. But Ernest, if you have a question, you can just unmute yourself and ask a question. You don't need to raise your hand. Right, so first we're going to do AB on one side, and then we're going to do BA on the other side, right? And we're going to see if they come out the same, right? Multiplication of numbers is always the same no matter which order you do it in, right? If I have two numbers, x and y, x times y is equal to y times x. But let's see if this happens with matrices, right? So with matrices, we have 1, 3, 0, 5, and maybe I'll write it like this. I'm going to multiply it with -1, 1, 2, 0. And so I want to know what's going to come out here on the product. So how do we get the entries of the matrix? Does anybody want to answer for the product? Well, so maybe I'll recall how to do the first one, and then one of you can do the second one. So remember, how do we get like the top left entry? We have to take the dot product of 1, 3 and -1, 2. Right? So that's going to be 1 times -1 plus 3 times 2. A little wider. And then down here, I'm getting the dot product of 0 and 5 with -1 and 2. So we get 0 times -1 plus 5 times 2. Then over here, similar thing, but we use the second column. So here we have the dot product of 1, 3, and 1, 0. So that's 1 times 1 plus 3 times 0. And lastly, we have the dot product of 0, 5, and 1, 0. So that's 0 times 1 plus 5 times 0. And if we simplify this and write everything out, we get, so that's minus 1 plus 6, so we get 5. And then down here we get 0 plus 10, so that's 10. And then 1 plus 0 is 1, and then 0 plus 0 is 0. So this is the answer for the product of the two matrices given in this order. If we do A and then A times B, their product is this new matrix, same size, but different numbers, and the numbers are 5, 1, 10, and 0. Okay. All right, any questions about this calculation, how we did it? This is just a review of how we did the matrix products from last week. Rufus, is that a question? Okay, no questions? Everything's fine?
Yes, everything is clear.
Good. Okay, so now let's do the other way, right? So the other way, what do we have? We're going to do minus 1, 1, 2, 0, and we're going to multiply this by 1, 3, 0, 5. Oh, sorry, I did the wrong order. Sorry, 1, 1, 1, 0, 3, and 5. Right. So, okay. So we wanna get what's going to be in here. So what are we going to get for the first entry in this matrix? This top left entry. Anyone want to give an answer? Yes?
Yeah. Let me try that.
Yeah, Princeton.
We take the minus 1, we multiply by the 1 that is up there.
Right.
And we take the 1, we multiply by 0.
Mm-hmm. And we add them,
and
right?
We take the 2, we multiply by the 1.
Mm-hmm.
And then we take the 0 and multiply by 0.
Perfect.
And then we take the 1 again, multiply by that 3.
So it's the minus 1 by the 3, right?
Minus 1 multiply by 3. And 1 multiply by 5.
Right.
Take the 2 and multiply by the 3 and the 0 and 5.
Perfect. Thank you. Yeah, that's exactly right. And so if we simplify this, what do we get? We get minus 1 up here, 2, and then here is minus 3 plus 5, so that's 2. And here's 6 plus 0, so we have 6, right? Right, so this is the answer. So thank you, Princeton, that's perfect, right? And so what we see here is we get two different answers, right? If we do it in one order, we get this matrix 5, 1, 10, 0. We do it in the other order, we get minus 1, 2, 2, 6, right? So these are completely different answers, right? They're not related at all. They don't even look at all like each other. So the moral of this story is that the order matters for matrix multiplication. Right, the order matters for matrix multiplication, or to state it a little more mathematically, it says that matrix multiplication is not commutative. Okay. So yeah, so matrix multiplication is not commutative. Okay, so it does matter what order you do it in. Sometimes you'll get the same answer, but usually you won't. Usually it matters which order you do them in. Okay, any questions on this problem?
Yeah, that overs.
Yeah, James.
Yeah, you are talking about the other matters, and the reason you seeing that we having different answer because of the sun, we having minus. So
Yeah.
if you are having still positive, will answer not be the same?
Exactly, yes. Even if the entries are all positive, they still won't be the same. Yeah, and you can try this as an example. We won't do it now, but if you change this -1 to a 1, you can try to do the same problem. Like change this to a 1 and then multiply them in both orders. And you're going to see that you still don't get the same answer. So the order really matters. Like basically any two matrices you write down, unless you do something silly, like, okay, if one of your matrices just has zeros everywhere, then you multiply it by some other matrix, you're going to get 0, no matter what the order is. But if you write down most matrices, I write down any two matrices and I kind of just write the numbers randomly, you will almost never get the same answer when you switch the order. Okay, it has nothing to do with this being negative. It also holds for anything positive. Okay, good. Other questions?
So, but Andrew,
Yep, Princeton.
so one case if we are doing even addition, so it means the order, it will be the same, the order will matter or it will not matter?
No, so
Because
with addition, it doesn't matter, right? So if you add two matrices, then the order doesn't matter. So for
Okay.
addition, it is commutative, but for multiplication, it's not commutative.
Okay.
Yeah, so for addition, it doesn't matter what order you put them in, but for multiplication, it does. So it's a way that matrices are different from numbers.
Okay, thank you.
Okay, you're welcome. Other questions? Okay, let's go to the next problem. So this was compute the inverse of 1, 2, 3, 4. So let me just recall the formula that we did last time. So recall that the inverse of A, B, C, D, this is equal to 1 over AD minus BC times the matrix. Well, we switch the A and the D, and we negate the B and the C. Okay. So this was the formula. This is the formula. Right. So this is a straightforward question. We just have to plug it into the formula, right? So if we compute this inverse, and of course, what we need also here before we do the answer, you need that AD minus BC is not equal to 0 because you don't want to divide by 0. So this formula only works if AD minus BC is not equal to 0. Okay. So, okay. So, so if we want to plug in this matrix to the formula, who wants to give, who wants to try to write down the inverse of this matrix?
Yes, let me try. But Andrew, it will be equal to 1 over 1 times 4 minus 2 times 3, which will be equal to 1 over.
Right, so 1 over
-2 is what
exactly. 1 over -2, but now we have the matrix also, right? So we need to fill in the matrix. This 1 over -2 is the factor that's outside of the matrix. So what do we get for the matrix now?
So we take that and multiply by the matrix. That is no.
Right. So which matrix, right? So our formula is we have to take this and we have to multiply it by this D minus B minus C A matrix, right? So if we're starting with 1, 2, 3, 4, what's the new matrix that we do here? Yeah, Armstrong?
Yes.
Yeah.
Yes. We said 1 was -2.
Yep.
Onto 4
Mm-hmm.
-2
Mm-hmm.
-3 1.
Yep. Great. Perfect.
Now
So
we say
four-
that will be equal to
exactly. So this is going to be what?
4
Yeah.
-2
Mm-hmm.
-3 1.
Right. Exactly. So that's how we've written it down. So 4 minus 2 minus 3, 1.
Divide by
Yeah.
divide by -2.
Right.
Then the final answer will be
Yep.
-2
Mm-hmm.
1
Yep.
3 or 2
Yes.
-1 or 2.
Okay. -1/2. Oh yeah. Wait. Sorry. I wrote this down wrong. Great. Perfect. Okay. So this is the final answer. All right, perfect. Right, exactly. We get -2 and then 1 and then 3/2 and then -1/2. So this is exactly the inverse matrix over here. Okay. Yeah, so it's just use the formula and it's pretty straightforward. You have a negative number here, but that's okay. It doesn't matter whether it's negative or positive. You have a scalar out here. It just gets multiplied by every entry of the matrix. And you wind up with exactly this: -2, 1, 3/2, -1/2. Okay, so everybody okay with this? Any questions?
Robert,
Yes.
like you have A, B, C, and D. It's the same way the normal arrange 1, 2, 3, and 4. So 4
Right.
is for D.
Yeah. So in this case, right, we have like A is equal to 1, B is equal to 2, C is equal to 3, and D is equal to 4.
I get it clear.
Yeah. Right. So the A always just means whatever number's in the top left. B is the top right. C is the bottom left. And D is the bottom right. Okay. Other questions? Okay. So let's go to the next problem. So the next problem we have, if A is this matrix, we want to, and B is this matrix, we want to show that AB equals I2. Remember what I2 is. This was the 2 by 2 identity matrix that's given by this matrix 1, 0, 0, 1, right? So we want to show that their product is I2. So let me just write this down: 2, 4, 3, 2, 5, 2. And then we're going to multiply it up here by -1, 0, 1 and -2, 1, 0. And so what happens when I multiply these? So just for time, I'm going to do this. So what do we have? We have the 2 times the -1 is -2, plus 4 times 0 is still -2, and then plus 3 times 1, which is going to be -2 plus 3, which is 1. So we get a 1 over here. 2 times -2 is -4, plus 4 times 1, which is 4, so they add up to 0, plus 3 times 0 is 0. So we're going to get a 0 here. And now we do the bottom row times the first column. So 2 times -1 is -2, plus 5 times 0, 0, so still -2, plus 2 times 1 is 2, so -2 plus 2 is going to be 0. And lastly, 2 times -2 is -4, plus 5 times 1 is 5, so -4 plus 5 is 1, plus 2 times 0 is 0, so we get 1. Right, so I didn't write out every step, but you can do the steps on your own. And we find that when we multiply these two matrices, we get the identity. Now, the problem is that if you recall, definition, A and B are inverses if AB and BA are both the identity. Okay, so now with normal multiplication, this doesn't matter, right? Because if I have 3 and 1/3, then you multiply them together, you get 1. You get the multiplicative identity with 3 and 1/3, and it doesn't matter whether you do 3 times 1/3 or whether you do 1/3 times 3, right? You get the same answer, 1, both times. But with matrices, we've already seen that if you do them in different orders, that you might get a different answer, right? So if we want to know whether B is the inverse of A, we need to multiply them in the other order and see if we get the identity. So let me just do this. What happens if we do it in the other order? So if I have -1, -2, 0, 1, 1, 0, and I want to multiply it by 2, 4, 3, 2, 5, 2, well, first of all, I'm going to get a 3 by 3 matrix, right? Because this is a 3 by 2, right? This is a 3 by 2 times a 2 by 3, and you cross out the insides, and what you're left with is a 3 by 3 matrix. And so how do we do this? Well, -1, -2, dot product 2, 2. So that's going to be, I'll just do this a little quickly. You can check it on your own. So that's -2 plus -4 is -6. Well, and so who knows? I don't even have to do the rest, right? I mean, I don't even need to calculate. This is certainly not going to be the identity because my first entry here is already -6. And remember, the identity here is equal to 10001001001. Right? So the fact that I get a -6 here means that I'm already not getting the identity. Okay? And that means that these matrices are not inverses, because if you multiply them in the other order, you don't get the identity. So the matrices are going to be not inverses. Okay, so we multiply them in the other order, we don't get the identity. Okay. So so I'll just write that down. Not inverses because
Okay, so
BA
that's
is not equal to the identity. Okay, so even though AB is the identity, BA is something totally different.
yeah, Andrew.
Yeah, question? Yep. Yeah, Christopher?
Yeah. So does that answer the why or why not? By saying not inverses because BA not equal to the identity matrix, right?
Exactly. Yeah.
Okay.
Right. For two matrices to be inverses, their product has to be the identity in both orders. Both AB and BA. Both have to be the identity. And we know that for matrices, you've got to check both, because matrix multiplication is not necessarily commutative. So just because you know one order doesn't mean that you know the other order also.
You have to check for both.
You got to check for both. Exactly.
Okay.
Okay. Other questions? Okay, so that's good for homework. So let me do one other matrix operation that we're not actually going to use very much, but since people see it, it's something that's good to see. So this is called the transpose of a matrix. So if we have a matrix A that's an m by n matrix, we define the transpose is going to be an n by m matrix. So you switch the rows and the columns, and it's given by switching the rows and the columns of A. So the example, right? So the example is, if A is equal to 1, 2, 3, 4, 5, 6, then A, the way we write transpose is we put a little T on top of the A. So this is read A transpose. A transpose, this is equal to, well, we started with a 3 by 2 matrix, 3 rows, 2 columns. So instead, we're going to have a 2 by 3 matrix, 2 rows, 3 columns. And what happens is what was the first column of A is going to be the first row of the transpose. So we write 1, 3, 5. And then what was the second column of A is going to become the second row
Hello,
of the
man. How you
transpose.
doing?
So we get 2, 4, 6. Okay. Is that a question, Armstrong?
No, no.
Okay, that's okay. Okay, so this is transpose, and sometimes a matrix is equal to its transpose. So if we did another example, if I have A is equal to like 1, 3, 3, 5, well then A transpose, it's still going to be a 2 by 2 matrix. Well, the first row here becomes the first column here becomes the first row. So the 1, 3 becomes 1, 3, and then the second column becomes the second row. So 3, 5 becomes 3, 5. And we see in this case, A equals A transpose. And so a matrix A where A equals A transpose, if this happens, this is called a symmetric matrix. Okay, and symmetric matrices are used a lot in multivariable statistics. So I don't know if we'll really get into that much, but it's good to at least see right now so that you can take the transpose and usually you get a different matrix. But if you happen to get the same matrix, so for a matrix like this, like 1, 3, 3, 5, when we take the transpose, we get the same matrix, then that is called a symmetric matrix. Okay. All right, any questions on this? Okay, good. Okay, so let's talk about the real part of the lesson for today. So, well, matrix multiplication we already recalled. So we want to talk about a specific kind of matrix multiplication, which is called matrix vector multiplication. And this is why this is going to bring matrices and vectors together. And I'll say that this is really why matrices were invented, was to be able to do this. So what is it? So suppose that we have an m by n matrix. We have A. And so we can always multiply it by another matrix B. And one of the most important cases to do it is when the matrix B is a column vector. Remember, we can think of a column vector as an n by 1 matrix, right? It has n rows, but only one column, right? And so in this case, what do we get for the product? Well, if A is m by n and B is n by 1, then for the product, remember, we cross out the n's and we're going to end up with an m by 1 matrix. Yes, sorry, question?
No.
No, okay. Sorry, okay, let me just mute everybody. Okay, so when we multiply A by this column vector, we get an m by 1 matrix, okay? And since it's an m by 1 matrix, we can also think of it as a column vector, right? So we kind of input a column vector, and then we multiply it by A, and the answer, the output, is another column vector. So one way of thinking about this is you can think of multiplication by A as being a function, right? What's a function? A function is just anything that takes an input and gives you an output. So you usually think of functions where the input is a real number and the output is a real number, and that means it's a graph that you can draw and it passes the vertical line test. But more generally in math, a function is any sort of procedure that takes an input and gives you an output, gives you a unique output. That's what a function is. Okay? So we're going to talk about this as a function where the input is a size n vector, right? Because we have to multiply A by a size n vector. And the output is a size m vector. Because when I do A times a vector, our output is a size m vector. And so this is sometimes notation when we talk about the set of all size n vectors, we write it like this. This is pronounced Rn or R to the n. So this is pronounced either Rn or R to the n. Okay, usually we just say Rn. And so what's going on is that what we say is that multiplying a function by multiplying by a matrix A, by an m by n matrix, it gives a function from Rn to Rm. Okay, so this means that if your input is a size n vector, so it's in Rn, then your output is a size m vector. That means it's in Rm. And if A is a square matrix, so it's n by n, then if your input's a size n vector, then your output is also a size n vector, right? And these square matrices are going to actually be the most important kinds. And so this type of function, we have a couple of names for it. Sometimes you'll see it called a matrix transformation, and sometimes it's called a linear transformation. They mean the same thing, okay? At least, for what we're doing, they mean the same thing, okay? So this is a lot of words, so we should see an example. I think I have an example on the next stage, right? Okay, so the example on the next page is, so here we want to just evaluate this, right? And usually we'll give the matrix a name. The matrix is going to be called A, and here the vector is going to be called V. Okay, so I could call it a matrix, right? A matrix, if this matrix is a 2x1 matrix, I could call it B for a matrix, but since I can also think of it as a column vector, often we'll write V. We'll give it a name that's actually a vector name, right? And so I'm going to evaluate this two different ways. Okay, so the first way is just what we have for usual matrix multiplication, right? This here is 2 by 2, and this is 2 by 1. So the product is going to be 2 by 1. Let me write that in blue. So the product is going to be 2 by 1. Okay. So what's the first way of multiplying these? Well, we know that what we get here is it's going to be a 2 by 1 matrix. The first row, the first entry is going to be 1, 2 dot product with 4, 6. So we're going to get 1 times 2, sorry, 1 times 4, 1 times 4 plus 2 times 6. And for the second entry, we're going to get the bottom row dotted with 4, 6. So we get 3 times 4 plus 4 times 6. And this is going to simplify to, so that's 4 plus 12 is 16, and 12 plus 24 is 36, right? So this is the answer. It's 1636. But there's another way of doing this, which is often a very good way when you're doing a matrix times a column vector. And that's called the column method. What's the column method? So if we want to do the column method instead. Sorry, I'm just going to mute everybody. So it's quiet. Okay, so the column method instead tells us what? Well, we know the answer is 1 times 4 plus 2 times 6, and then 3 times 4 plus 4 times 6. So if I want to, I can write this as 4 times the vector 1, 3, plus 6 times the column 2, 4. Right? So if I want to multiply, and then, we get the same answer here, right? We get, if you do this all together, you're going to get, 4, 12 plus 12, 24, which is going to be equal to 1636, right? It's going to be the same answer. But the idea here is that if I have a matrix and I want to multiply it by a vector, so if the vector is 4, 6, one way that I can do that is take the 4 and multiply it by the first column of the matrix, and then take the 6 and multiply it by the second column of the matrix, and then add them together, right? So what's going on here is this is the first vector entry. This here is the second vector entry. Okay, this here is the first matrix column. And this here is the second matrix column. Right? So what we see is you can, if you want to multiply a matrix by a vector, you can do it in the standard way and you get the right answer. But you can also do it by taking each entry in the vector and multiplying it by the corresponding column. So I can take the 4 times the vector 1, 3, and then the 6 times the vector 2, 4, and add them together. And if you do this, you're going to get the same answer. You're going to get 1636. Okay, so this is the summary. So we can evaluate a matrix vector product by adding up the columns of the matrix, each multiplied by the appropriate entry in the vector. Right, so I take the first column multiplied by the appropriate entry, which is 4. And then I take the second column multiplied by the appropriate entry, which is 6. And if I add those all up, I get 16 times 36. Okay. So in this case, we could write that AV is equal to another vector W, where W equals 1636. Okay, any questions about this?
So, yeah, but Andrew,
Yeah, Princeton.
so it's compulsory to have 2 by 2 matrix and multiply by 2 by 1. It can't
No, it is
be.
not. It is not compulsory to do that. All that needs to happen is that the size of the vector needs to be the same as the number of columns of the matrix. So I could
Okay.
have a 3 by 4 matrix and multiply it by a 4 by 1 vector. That's fine, as long as the number of columns of the matrix is the same as the size of the vector.
Okay.
And we need that for this column method, right? Because each entry in the vector is supposed to correspond to a column, right? So the number of columns has to be the same as the number of entries in the vector in order to do the multiplication.
So yes, but Andrew,
Yep.
if we are going to have the second matrix, the 4 and 6, if we are going to have the 4, 2, and 6, so that means in our other corner of the matrix, we're going to indicate another row there.
Maybe I don't understand the question. Can you ask it one more time?
Yeah, like we got 4 and 6 in this matrix.
Right.
If we have 4, 2, and 6.
So if the
what we're
vector
going-
had size 3, so we had 4, 2,
Yeah.
6. Yep.
Yes. So will we be able to multiply by the other matrix, the 2, 1, 2, and 3, 4 to be
No,
exact?
we would need another column, right?
Okay.
Because if we had 4, 2, 6, we'd have a length 3 vector. And that
Yeah.
means that the matrix would have to have 3 columns to be able to do that. Yeah.
Okay.
Okay. Other questions? Okay. So maybe let me add another page before we go to this next thing. Let me just try to remember. Okay, that's okay. Okay, so let me add another page before we do this. So right, so in general, right, we could have another example. If I have A is some matrix that's like 2 by 3, like 1, 2, 3, 4, 5, 6, and then V is a length 2 vector. So we say that V is in R2. So sorry, if V is a length 3 vector, V in R3, then A gives a function whose input can be V, and the output will be a size 2 vector. right? Because the input is going to be V. You can multiply it by a 3x1 matrix or a 3 column vector. And then the product of them is going to be a 2x1 matrix or a vector of length 2. Okay.
Okay.
Okay. So maybe we'll just do one quick example.
Yeah.
So if V is equal to 1, 1, 1, then AV is going to be 1, 2, 3, 4, 5, 6 times 1, 1, 1. And let's use the column method. So this tells us that what we have to do is take the different columns of the matrix and multiply them by the entries of the vector and then add them up. So what we're going to get is 1 times 1, 4 plus 1 times 2, 5 plus 1 times 3, 6. And so this is just 1, 4 plus 2, 5 plus 3, 6. And this comes out to be 6, 15.
15.
Okay, so notice the input had size 3 and the output has size 2. That's because A was a 2x3 matrix. So the input is the number of columns and the output is the number of rows.
Okay, thank you.
Okay, so let me just say, yeah, so this is another example. Okay, so we want to talk about special examples. So if we look at 2x2 matrices here, so let's look at 2x2 matrices, right? So a 2x2 matrix gives a function whose input space, or the math word for that is the domain, is R2, and the target space, meaning the output space, we could call it the output space, is also R2, right? If it's a 2x2 matrix, you put in a size 2 vector and you spit out a size 2 vector, okay? So what we want to do, so the reason matrices are important is that they transform vectors into other vectors, right? That's how this process works. Like it transforms vectors into other vectors. And what we're going to see is that you can do all sorts of geometry with matrices. So you can have a matrix that's going to stretch vectors, and a matrix that's going to rotate vectors, and a matrix that's going to reflect vectors. And all of this geometry can be done using matrices. So we're going to see that in some detail next week. But for this week, we just want to do some basic things. So what you can write this in is you can say that A, as the matrix, it sends you from R2 to R2. Okay, this just means that if you take an input vector of length 2, you multiply it by A, your output vector also has length 2. So here's a question. So I'm going to have here functions. So functions, and then over here, I'm going to have the corresponding matrix. Okay, so here I'm going to write down 4 functions. I have what's called the 0 function, which just means that every vector goes to the 0 vector. I have the identity function. Please keep yourself on mute unless you're asking a question. So I have the identity function, which means that every vector goes to itself. Then I have the doubling function, which means every vector is going to go to 2 times itself. And lastly, I have the mirror image function, where the input is a vector and the output is the same vector, but pointing in the opposite direction. Okay. So first of all, the 0 function. What matrix do you think gives the function where if you input any size 2 vector, the output vector is always 0? What matrix do you think is going to do that?
This is going to be an identity matrix.
Sorry, I'm not getting you so clear. Can you say that again?
Is it going to be an identity matrix?
It's not going to be the identity matrix. So the identity matrix will give you one of these functions, but it's not going to give you the 0 function. Which one do you think it will give you? So if these are 4 different functions, so the identity matrix, you said, right. So the identity matrix will actually correspond to the identity function. So it turns out that if you take the matrix 1, 0, 0, 1, so let me just draw lines here to separate all of these. So it turns out here that if you take the identity matrix, so this 1, 0, 0, 1, and you multiply it by a vector x, y, what's that going to be equal to? Well, we can use the column method if we want. This is going to be x times the vector 1, 0 plus y times the vector 0, 1, right? X times the first column plus y times the second column. And this just becomes exactly the vector xy again. All right, so we see what the identity matrix gives us. It's one of the reasons it's called the identity matrix, is that if you multiply it by xy, it gives you xy again. So your input is the same as the output. So this is the identity function. I'll write the matrix in red. Just again, 1, 0, 0, 1 is the matrix that gives the identity function. So what matrix do you think gives the 0 function? That no matter what vector you put it in, if you multiply by that matrix, you end up getting the 0 vector. So what matrix is going to turn every vector into the 0 vector? Someone have a guess?
I don't know what I would say. Geometric. Keyword has geometric.
Exactly, right? So in this case, if we take the matrix where every entry is a 0, well, 0, 0 times any vector xy is going to be x times 0, 0 plus y times 0, 0. And we know that that's just 0, 0, right? That's just the 0 vector. Right, so this is just 0, 0. And so this is the 0 function, right? It sends every vector to 0. And so the matrix that's going to give us the 0 function is just the 0 matrix, 0, 0, 0, 0. Okay, any questions on that? Okay, what about the doubling function? Okay, so we want a matrix that if we multiply it by a vector, it's going to give us twice that vector. So here was the identity function. If I inputted the vector xy, my output was also xy. So I want to make a matrix that if I input xy, the output is not going to be xy, but instead it will be 2x and 2y, right? So it's going to double the vector. So does anybody have a guess what matrix they think is going to be so that if you plug in xy, your output is 2x, 2y?
Can it be identity for Andrew?
Well, the identity we already have, and that when you plug in xy, it gives you xy. So what do you have to modify about the identity so that instead of getting xy as your output, you'll get 2x and 2y as your output?
So I think
let me guess.
addition of
Can I guess, Andrew?
Yep. Sorry. Yes. Christopher.
They're going to be scalar product.
Sorry. Say that again.
They're going to be scalar product.
Yeah. So I think I'm not sure I heard you. I think the signal is bad, but what we want is 2 times the identity. Right.
Scalar product.
Yeah. I'm sorry. I'm not getting you clear. The sound is not good. So what we do is if I take the matrix, which is like the identity, but I multiply everything by 2, right? So 2002 times xy is going to be, well, what do I do? That's x times the first column, which is 20, plus y times the second column, which is 02. And this is going to give us 2x and 2y. Okay, so the matrix that's going to double everything is going to be this matrix 2002. Right, this is the matrix. Oh, scalar product. Okay, yes, exactly. It's the scalar product of 2 times the identity matrix. Exactly. So right, so 2002 is exactly what we want here. Okay. So lastly, what about the mirror image function? We want a matrix that when we multiply it by xy, we get, in the end, we're going to get minus x minus y. So what do you think we should do to the identity in order to get that?
The inverse.
Right, so we invert, but what should be the entries in the matrix here?
Yeah, bro.
Yep.
Yeah, that'd be 1, 0, 0, 9, 1.
Exactly, right. So -1, 0, 0, -1. Because this is going to give us x times -1, 0, plus y times 0, -1. And that's going to give us minus x minus y. So the matrix that we want is -1, 0, 0, -1. Okay, so these are some examples of matrices that do things to vectors where the geometry is very well understood, right? The first one takes every vector and turns it into 0. The second one takes every vector and doesn't do anything to it. It just keeps it fixed. The third one takes any vector and stretches it by 2. And the fourth one takes any vector and flips it around. It turns it the other way, right? So next time, we're going to see more complicated matrices that can take a vector and say rotate it by 30 degrees. Or it can take a vector and you have some other line and it can reflect the vector across that line. So this stuff is also done by matrices, but it takes a little bit more work to figure out which matrices do what. Okay, but for now, we have these kind of simple examples of matrices that they take a vector and they output a different vector where the map can be described easily. There's the 0 function, the identity function, the doubling function, or the mirror image function. Okay. Any questions on this?
It's okay, bro.
It's clear. Okay, great. Okay, so let me say just a couple of more general properties. I think we won't have time to do the proof today, so I'm going to save the proof until next time. So we'll prove the addition law using the column method. This is going to be next time. But so the addition law tells us that if I have a matrix and I multiply by a sum of 2 vectors, it's just the same as the matrix times the first vector plus the matrix times the second vector. Okay, so you can also think of this as the distributive law, the same thing. And then we also have the scalar multiplication law, which is saying that if I take a vector and I multiply it by a scalar, and then I multiply it by a matrix, it's the same as multiplying the vector by the matrix and then multiplying it by the scalar. So for instance, if I have A and I want to multiply it by 2V, that's the same thing as doing AV first and then multiplying the answer by 2. Okay. So this just means that you can take a scalar if you want to, and you can always pull it out behind a matrix. Okay, you can pull it out. So ACV is the same thing as CAV. And really here, I guess I should probably have parentheses around the AV.
Another way to see, Andrew?
Yes, question?
No, another question, just look clarity on this. So another way to see is that you can factor out a question.
Sorry. If is whoever's not speaking, I need to put you on mute because I can't hear. Yeah, sorry, Christopher, ask your question again.
It's not a question. I'm saying just little clarity on the additional information. You're saying putting out the scalar and multiplying the vector the matrix by the vector. So I'm
Right.
saying another way you could say is that you can factor out the scalar and multiply the matrix by the vector and then multiply by the scalar later, right?
Right. Yeah, you can do that also. Yeah, so
factor
you can do this also. You can multiply the matrix by the scalar and then times the vector. All of them are the same.
Okay.
Yeah. Okay, so we're going to prove this next time. For now, let's just allow it. And then the last thing I want to say, because I do have to get off in a couple of minutes, is that you can actually combine the addition and the scalar multiplication laws. And you can show that if I have any two vectors and any two scalars, if I do A times CV plus DW, I can get CAV plus DAW. And the reason for this is, right, if I have AV plus A times CV plus DW, I can use the addition law. And that's going to give me A times CV plus A times DW. And then I can use the scalar multiplication law. And that's going to then give me, that lets me pull out the scalars. And so that's going to give me CAV plus DAW. Okay, so this is a kind of general law that combines both the addition law and the scalar multiplication law. So it just says you can factor, you can pass addition and scalar multiplication through matrices, right? You can factor this out into two separate pieces, and then you can pull out the scalar. Okay. All right, so I do need to finish now. So just there's going to be 3 homework exercises. We'll finish next week. So one is just straightforward. You have to multiply this matrix by this vector and say what the answer is. The second question asks, is there a matrix that if the input is a vector xy, the output is going to be this new vector where you add 1 to both x and y? So this is kind of a yes or no question. And then the third one is, let's say you have a 3x3 matrix and you know that A times 1, 2, 3 is 1, 4, 7. And you also know that A times 2, 1, 5 is 2, 3, 0. The question is, can you figure out what A times 3, 0, 7 has to be? And the reason this is hard is because I'm not telling you A. I'm just telling you that A times this vector is this vector, and A times this vector is this vector. And I want you to tell me what is A times 3, 0, 7. Okay, and the hint here, so hint is to use the addition and scalar multiplication laws. Okay. So I will send out these notes and the recording for everybody. So thank you as always for your attention. And next week, we're going to discuss more about the geometry of linear transformations in 2 dimensions. And in particular, we're going to discuss matrices corresponding to rotations and reflections, which are 2 of the most important linear transformations. Okay, so I'm going to stop the recording here.